Welcome to day 10 of the macOS and iOS Security Internet Advent Calendar. Good to have you back. Today we will have a little look into the Kernel Address Obfuscation, which is a mitigation Apple introduced to the kernel a while ago. So the problem was that traditionally there's a lot of API functions or API methods that leak kernel addresses to user land. So there is a bunch of APIs for debugging purposes like machport kobject, machport space info. Then we have VM region recurse, VM map region recurse, vmap page info. But we also have system calls like proc info for retrieving information. We have the fstat system call that, for example, in various cases returns kernel addresses as fake inode numbers, for example. Then we have the whole sysctl interface where there's a myriad of variables that can be queried from user land, and some of them basically contain kernel addresses. So that used to be not considered a security problem, especially because the kernel was at a static location and the kernel binary was known, so there was no secret addresses in the kernel, and also the heap was not really randomized so much, so that knowing addresses was not such a big deal in the past. But then came iOS and stuff got more important, and we got KSLR in iOS 6, and now suddenly leaking addresses in kernel land to user land processes is a big deal, because we don't want KSLR be broken by simply, for example, querying a sysctl interface. So, and because of that, Apple started to mitigate this problem since macOS Mavericks, or also known as iOS 6. So the way Apple did this was they introduced a new macro to the kernel source code, which is VM kernel address perm. And this new macro, as you can see here on the slides, they basically added the variable VM kernel address perm to the input. Only null pointers would be returned as null pointers, but everything else, the address perm would be just added. And if I recall correctly, they forced the lowest bit of the address perm variable to be 1, so that nothing plus this address perm could ever be by accident 0. So the idea here now is that this VM kernel address perm is a 64-bit secret value. This is the same value for all pointers. It is one time created at boot, just as a random value that is added to a pointer. The result of this is that now every instance where a kernel address is returned to user land, we use this macro, and the pointer will not be a plain text kernel pointer anymore, and we still have the ability to see different pointers for what they are, different pointers, but we don't know exactly where they're pointing to in kernel land. That's what we actually wanted to achieve here. So in some cases, Apple realized that when they return certain addresses, the addresses are actually not just heap pointers and so on. In some cases, the pointers are actually directly pointing inside the kernel image itself. For example, there's this case of the real host, which was famous because there were, in some cases, the pointer to the real host returned to userland. And the problem here is that this is a pointer inside the main kernel, and let's assume you could break the obfuscation for whatever reason, then you automatically would have broken also KSLR, because you would know the decoded pointer and you would know the original pointer from the original unslit binary. And for these cases, Apple created a second case where they basically have this macro VM kernel unslide, what basically does nothing else than remove the KSLR slide from the pointer, but only if it is detected as being a relocated pointer. Over the years, Apple had various problems in detecting if something was unslid, it needed to be unslid or not. So there have been security vulnerabilities where people have tricked this whole system by stealing addresses that way. But nowadays, Apple has made this more and more robust by basically changing this and hardening these macros. So, but still, the way their obfuscation works has some security weaknesses. First, let's have a look at what the obfuscation is on a mathematical level. And when you look at it, you basically have an obfuscated pointer is the original pointer plus the secret value. As I said earlier, the secret value is a 64-bit value that's created at boot time, one time randomly. So the secret value is basically the same for every single pointer that the kernel returns to userland. And because of that, a single instance where an attacker can get the obfuscated pointer and the plaintext pointer will completely break the system, and so that should never happen, because otherwise automatically the whole protection is broken. Throughout the history of the last few years, there have been numerous of these public and non-public exploits that make use of this, but basically that's the idea, one single instance and it's broken. But there was more actually to this weakness that might be obvious when you look at the mathematics a little bit deeper. And even if you don't know the secret value, you need to keep in your mind what is happening when you have an obfuscated pointer 1 and you have an obfuscated pointer 2. They obviously have different values, so there's a delta in between these two obfuscated values. So now if you open up what the obfuscation means, you have pointer 1 plus the secret value equals pointer 2 plus the secret value plus the delta. That's just simple mathematics. Now, when you look at this, you can eliminate the secret value on both sides of the equation, and you realize that pointer 1 is equal to pointer 2 plus delta. So what does it mean? It basically means that the delta of two obfuscated pointers and two non-obfuscated pointers is the same. So this means you can see actually through the obfuscation how far away two pointers are from each other. And with multiple pointers being leaked and so on, you can actually determine their relative location in kernel land, and you can also find out which is the first one and the next one and so on. And this can be already good enough for having like fine-grained heap layouts and stuff like that, because you can basically read their delta from the obfuscated value itself. This is obviously bad, and so Apple needed to react in a way. And this was basically the birth of new and better macros. And Apple has added this whole block here to the, I think it's the vmparam.h file, where they document quite detailed what of these macros is secure and which of the macros are not secure. And so Apple is now favoriting a new macro which is called VM kernel address hash. So what is VM kernel address hash? When you look through the source code of the kernel, you will realize it's basically a wrapper around the function VM kernel address hash, and this again is a wrapper around VM address kernel hash, VM kernel address hash internal. And when you look at the function, you will basically see that this function is initializing a SHA-256 cryptographic hash, and what it feeds into the hash is basically a salt. The salt is also a totally random 64-bit value, and it feeds in the address. And regarding the address, it will actually detect if the address was ASLR slid or not, and if it was, it basically removes the ASLR slide and returns the address instead. So the hashing will only be done on actual real addresses that are not coming from inside the kernel binary. So the moment something comes from the heap, for example, it will be digitally hashed, and it's using the 64-bit salt here because it means you cannot really break the obfuscation unless you have the ability to somehow brute force a 64-bit space, which is not feasible. And the return value here is basically the first 64-bit of the hash, and this is then the pointer that is returned to userland. So in theory there is the possibility of collisions, but it's quite low in this regard. And so this means that basically every single 64-bit pointer should result in a different 64-bit output here, so that you can see the same pointer through the obfuscation, but you cannot make any guesses about the distance between pointers whatsoever, because they're all basically cryptographically hashed. So, and all that said is, you must know that this new macro is very strong. But when you look at the actual kernel source code, you will see that the old macro is still used in various places. And of course, mitigations are only as strong as your usage of them. So if you don't really use the new feature, then it stays weak as before. So let's look at the recent kernel and see where the new and the old macros are used. So I will just look for the new macro, and when we look for it, we can see, okay, here directly there's a usage in the sys pipe, and this is basically the inode number of a pipe. So when you ask an fstat on a pipe, you will get a fake inode number, and that is the address of the pipe in memory. And so this one is now protected, and the reason why this is now protected is quite likely because these pipes were used in public and maybe also non-public macOS and iOS exploits that Apple is aware of course. And so you can see the pipe part here is actually protected that way. There's also some other usage here, 1, 2, 3, 4, 5, 6 times here. Then we have code for actually making this available. We have the header file, we have the actual implementation itself, and another header file. So you can see it's just basically used like in 6 different places or so. That's not much when you think about something like a huge kernel. So that's why we can just look for the other one, the address perm, and let's do this again. Let's delete the result here and try this again. And then now you can see that we have here a bunch of debugging code. So usage of this in a debugging code is not so problematic. There's a lot of these debugging codes that use the old macro. So like I said, this is all not really a big problem. Here are some printfs that will likely end nowhere on a production kernel. And But here we will finally see some code. This here is from a sysctl handler. So here are some addresses where the old macro is still used via the sysctl interface. And when we continue looking through this, we will see that in other cases, this here is also a sysctl interface. It's actually the same one or so. And when we go through this, we will see that aside from these error logging stuff, here, for example, this here is fill common sock info. So this information about a socket. So this is likely all coming from proc info. Yeah, when we look at who uses that, we will see it's fill socket info. And when you look at this, we will see this is used in the proc info system call. And yeah, so this is basically this part. And yeah, when we look through this, we will see that the address perm is used in a few more places and so on. So it's still used in various regions. So it's still possible that at least certain types of fee pointers can be leaked and broken that way. But yeah, of course, the exploit that we're using, the pipes, they will now no longer be able to use this for a pipe. But yeah, there's still some places where it's used. Just the one that was obviously notoriously used in exploits is now broken. Yes, so that's basically the idea behind this. So this is like a mitigation that when it's fully migrated to the new macros, will be basically not breakable that easy. Because like I said, you need to know the salt. Of course, if you know the salt, then you likely have it a little bit easier to break the mitigation. But if you know the salt, you would still need to brute force what pointer belongs to what input is resulting in what output. And so it's maybe possible with a very fast system or a lookup table and something like that. But it will be very unlikely, and for that you first need an info leak that allows you to steal basically the random values from the kernel. And if you can already steal random values from the kernel, it's likely easier to just steal the address itself than to try to steal something to break the obfuscation.